So this time we're going to be taking a look at section 8.7, which is about variation. And it's likely that you're familiar with variation even if you don't realize it. Now, there are lots of different situations in life in which this idea of variation comes up. But one situation that we could take a look at is, let's suppose someone has a job that pays $15 an hour. And in this analysis, we're not going to worry about taxes or overtime or anything like that. We're just looking at a straight $15 per hour rate. So each hour the person works, they get $15 added to their gross pay. So if you think about how the paycheck would be influenced by this, the larger the number of hours worked, the larger the paycheck. The lower the number of hours worked, the lower the paycheck. So if we were to take a look at Y as the amount of gross pay in this situation, then Y would equal 15, which is the hourly rate, times the number of hours, which is X. So in this particular case, we would say that Y varies directly as X, and in fact, Y is equal to this constant 15 times X. Now, when we talk about what's called direct variation, this is the kind of situation that we're going to be essentially taking a look at, is that Y is going to be equal to some non-zero constant times X. So let's take a look at the definition. Let's say we have Y is equal to K times X for some non-zero constant K. Then we say that Y varies directly as X. Or we could say that Y is directly proportional to X. Now, this K is what we refer to as a constant of variation or a constant of proportionality. So once again, this is a non-zero constant K, this is our proportionality constant, and the Y equals Kx is what we refer to as our direct variation equation. So think of this as more or less a translation. Now, if you think about maybe two different variables, let's say that we have R is directly proportional to T. All right. Well, over here we have Y is directly proportional to X, translated to Y equals K times X, for this non-zero proportionality constant K. So if we say that R is directly proportional to T, for example, then the translation would go something like this. We would have R is equal to K times T. Now, in some classes, I tell students, watch your language, and it's not as if they're cursing profusely in class. It's not that at all. It's that whenever you're given some sort of mathematical situation, language is very important. And so being able to translate, so for example, if you take a look at someone talking about a sum, okay, well then addition is what we're considering. If someone talks about a product, then we're looking at multiplication. So language is very important, and so when we see the language that one quantity is directly proportional to another, then we translate that into this mathematical equation. So let's take a look at some examples. Let's say that we know that Y varies directly as x. Okay, so y varies directly as x. Now, if y equals 5 when x equals 3, then we're going to try to figure out an equation for x and y. All right. So this example isn't altogether too bad. We're given at the very beginning that y varies directly as x. Y varies directly as x, once again, same as y is directly proportional to x, which means that we're dealing with this translation into the equation y equals kx. So let's start with that. We'll have y is equal to k times x. Now, you don't want to stop there because we don't actually have the specific value of k determined at this point. However, we do know that y equals 5 when x is equal to 3. So we can go back to this equation, plugging in 5 for y, and plugging in 3 for x. And we get 5 is equal to k times 3. Now, you might want to look at that as 5 is equal to 3k, and that's fine. But the goal right now is to actually solve for k, in which case we need to divide both sides of this equation by 3. And that'll give us k is equal to 5/3. So we now know what our proportionality constant is. Well, if k is equal to 5/3, we can then go back to this more general equation, plug in the 5/3 for k, and that'll give us our answer to the particular situation here. So we'll have y is equal to 5/3 x, and that is our equation for x and y. Now, we could do things like using an equation like this to figure out other relationships between x and y. So, for example, we might say if y is equal to 12, then what is x? Or what happens to y if x is equal to 17? And these are all things we can figure out once we know the value of k is equal to 5/3 here. But let's take a look at another example in which we have a couple of different quantities, and we're going to be looking at direct variation yet again. So for this example, we're going to take a look at two other quantities, call them w and t. And let's suppose that we know that w varies directly as t. We're going to be given some sort of information about w and t, and then we're going to be asked to figure out what the value of t is for another value of w. So starting out with, if w is equal to 7, when t is equal to 2, we're going to find t when w is equal to 9. Now we're going to start this example pretty much the same way we started the previous one. Obviously we're not using x and y because the w and t are given here instead. But we are going to realize that w varies directly as t is going to translate into the same type of equation we have here. It's just that we're going to get w is equal to k times t. We're given that w is equal to 7 when t is equal to 2, and that's going to enable us to figure out the specific value of k that fits into this particular framework. So we'll have 7 plugged in for w, we'll have 2 plugged in for t, and perhaps you would prefer to have the right side written as 2k, that's fine. So if we have 7 is equal to 2k, we would divide both sides of this equation by 2, and we get k is equal to 7/2. So from this, we know that k is 7/2 now. We can plug the 7/2 in for k, and get our specific equation, which is going to be W is equal to 7/2 t. So for this part, when we're asked to find t when W is equal to 9, that means we need to go into this equation, plugging in 9 for W, and then we can solve for t. And so I'm going to do that over here. We're going to have 9 is equal to 7/2 times t. And at this point, if you wanted to, you could multiply both sides by 2/7, or you can take a couple of steps to really accomplish the same thing. And so here we would double both sides, let's say. 2 times 9 will give us 18. And then if you take 2 times 7/2, that gives you 7. And that's multiplied by t, so we have 18 is the same thing as 7t. So to get t, we would divide both sides of this equation by 7. And so 18 over 7 would be our value of t when W is equal to 9. Now I'd like to show you one more example in which we take a look at this direct variation. So this particular example is going to essentially relate the bounce height of a tennis ball to the drop height of that same ball. So suppose that the bounce height B, which is going to be in inches, of a tennis ball varies directly as the drop height. And this drop height that we're going to use we'll call D, and it will also be in inches. Alright, so what we have so far, once again, is the bounce height, capital B, in inches, of a tennis ball varies directly as the drop height D, which is also in inches. Well, if you think about what we have so far, and consider the translation that we make in terms of direct variation, we're going to have B is equal to K times D as our equation. Now the bounce height of the tennis ball is 20 inches. When the ball is dropped from an initial height of 30 inches. So then we're going to have a couple of different questions to figure out here. The first question is, what is an equation for B and D? And then the second part to all this is going to be for us to figure out what the estimated bounce height is if the drop height is 50 inches. All right, so got a little bit of stuff going on here, but if you think about it, we're really going to be approaching this problem in much the same way that we approached these particular problems. It's just we have a little bit more of a description of what's going on with a specific example. So let's take a look at our Alright, so once again, got this bounce height capital B of a tennis ball, varies directly as the drop height D. So if we're wanting to find an equation for B and D, so part 1 we would have B is equal to K times D. Now, we need to know what the value of K is that pulls everything together here. And that's where this next part comes in. It says the bounce height of the ball is 20 inches if the ball is dropped from an initial height of 30 inches. Okay, well remember the bounce height is B, so if we know that B is equal to 20, then we know that D is equal to 30. And that means we would plug in 20 for B, we will plug in 30 for D, and if you'd rather have that right side listed as 30K, no problem, that works. We will then divide both sides of this equation by 30. That'll give us K on the right side, and then 20 over 30 on the left reduces down to 2/3. So now we know the proportionality constant K, which means that we can finish up this part 1. Finding an equation for B and D, we're going to have B is equal to 2/3 D. This is going to help us with part 2, estimate the bounce height if the drop height is 50 inches. Well, remember the drop height, once again, drop height is D. So this is sort of like the example that I have on the rightmost board here. We already have our equation involving B and D, but when we say estimate the bounce height if the drop height is 50 inches, what we're really asking is what is B when D is equal to 50? It's kind of like saying what is T when W is equal to 9? So for part 2, we already have the equation for part 1. So we'll go ahead and write that down one more time. B is equal to 2/3 D. But it's this bounce height B that we're trying to get an estimate for if the drop height D is 50. So what I would want to do is plug in 50 for D and then figure out what B is. That gives me 2/3 times 50 is equal to B, which means B is equal to 100 over 3. Take the 2 times 50 gives you the 100, and technically the 50 is over 1, so 3 times 1 will give you 3 in the denominator. So 100 over 3, that's 33 1/3 inches for the bounce height. So next we're going to take a look at a second type of variation. And that second type of variation is what we refer to as inverse variation. Now remember, with the direct variation we had y is equal to k times x for some proportionality constant k. This time with inverse variation we have y is equal to k divided by x for some non-zero constant k. So in that case, we say that y varies inversely as x, or y is inversely proportional to x. So y varies inversely as x, or y is inversely proportional to x. Now k is what we refer to as the constant of proportionality again. So once again, k is constant of proportionality. And on top of that, y equals k over x. is the inverse variation equation. Now, if you have some sort of positive constant k, then increasing x is actually going to mean that y decreases, while decreasing x would mean that y increases. So that there's that inverse relationship between how x and y are going to behave. So let's consider some examples. So for this example, we'll suppose that y varies inversely as x. So we're going to figure out if y is equal to 4 when x equals 2. Then what is an equation for x and y? So again, y varies inversely as x. So if y equals 4 when x equals 2, find an equation for x and y. Once again, we're looking at a translation. Y varies inversely as x translates to y equals k over x for some non-zero proportionality constant k. So we'll start with that y equals k over x equation. But we can figure out what k is by plugging in 2 for x and plugging in 4 for y. So we'll have 4 is equal to k divided by 2 in this case. But if you want to get k by itself, then all we have to do is multiply both sides of this equation by 2. So multiplying the left side by 2, 2 times 4 gives us 8. Multiplying the right side by 2, 2 times k over 2 is the same thing as k. So we get k equals 8 in this case. We can now take the 8, plug it into this more general form, and that will give us our equation y is equal to 8 over x. So that's the equation that we were looking for. Now, let's consider another example. So in this example, we're going to suppose that capital G varies inversely as R. So once again, this will give rise to a particular translation into the equation. In this case, capital G equals K over R. So let's suppose G equals 8 when R is equal to 3. So if capital G equals 8 when R is equal to 3, then what is R when capital G equals 4? So that's what we're going to want to take a look at. G varies inversely as R. We know G equals 8 when R is 3. That's going to help us figure out the value of K in our equation. And then once we have our more specific inverse variation equation, we'll be able to figure out what R is, knowing that G equals 4. Alright, so once again, G varies inversely as R. Translate that to G equals K divided by R. That's our general inverse variation equation for this particular situation, but we need to figure out the value of k that pulls all this together. And that's where the g equals 8 when r equals 3 information comes in. So we plug in 8 for g, we plug in 3 for r, and now we have 8 is equal to k over 3. So very similar to the situation we saw in the previous example. This time, if we want to get k by itself, we'll multiply both sides of the equation by 3. You'll have 3 times 8, or 24 on the left side, and then 3 times k over 3 will give us k on the right side. So we have k is equal to 24. We can then take the 24, plug it in here to the more general equation, and then that'll give us the specific inverse variation equation that we're looking for. So we'll have g equals 24 divided by r. Now, once we have that equation, we then take a look at this last part where they're asking us to figure out what r is when g is equal to 4. And so if you think about what's going on in this particular case, then you would have, well, g is equal to 4. So g is equal to 4, we'll have 4 is equal to 24 over r. Now I could think about, let's say, multiplying both sides of this equation by r. So if I multiply the left side by r, I would get 4r. And if I multiply the right side by r, well, 24 over r times r, the r's would cancel out, and we would simply have 24 on the right side. So that would give us 4r is equal to 24. And then we could divide both sides of that equation by 4, and that would give us r equals 6. So according to the situation we have here, r would be 6 when g is equal to 4. All right. So one thing to keep in mind, though, is that we had g equals 8 when r was equal to 3. So let's make a little bit of a note here. G equals 8 when r is equal to 3. But we also had g equals 4 when r is equal to 6. So what we see from this is when we decreased g from 8 to 4, r actually increased from 3 to 6. So this goes back to that idea that if you have a positive k here, decreasing the x is going to increase the y, increasing the x will decrease the y. Right. Well, I've got one more example I'd like to show you. And with this example, we're going to be taking a look at a more specific type of scenario. So this one is going to be an example in which we consider the weight of an object. So in this case, the weight of an object is going to vary inversely as the square of its distance from the center of Earth. So once again, the weight of an object varies inversely as the square of its distance from the center of Earth. So let's suppose that you have an astronaut that weighs 180 pounds. But that weight is going to be at sea level, which we're going to see is about 4,000 miles away from our center. Now, let's suppose that this astronaut is 2,000 miles above the Earth's surface. How much does the astronaut weigh then? Right, so again, the weight of an object varies inversely as the square of its distance from the center of Earth. We have an astronaut that weighs 180 pounds at sea level, which is about 4,000 miles from the center of Earth. So the question is, how much does the astronaut weigh when 2,000 miles above the surface of Earth? Now, this is one of those situations in which it's good to draw a picture. In fact, in many situations, it's good to draw a picture because sometimes it can help you figure out a better vision of what the problem is all about. And so in this particular case, we'll have Earth represented. We'll have the center right here. And we're going to take a look at this distance as 4,000 miles. Now, the astronaut is going to be 2,000 miles above the surface of the Earth. And so we're looking at the astronaut is somewhere over here. It's going to be an additional 2,000 miles. And so if you take a look at the total distance from the center of Earth, you're actually looking at 6,000 miles. So that's probably worth putting up here as well. Preferably with a marker that works. So once again, 6,000 miles, 4,000 plus the 2,000. Right. Now let's go back to the very first part of this example. So suppose that the weight of an object, well, let's have some sort of variable that represents the weight. We'll call it W. So let's say the weight W of an object varies inversely as the square of its distance. Okay, the square of the distance, if we call the distance d, then that's going to be d to the second power when we talk about the square of the distance. So the weight W is going to vary inversely as d raised to the second power. That is, W is equal to k over d squared. Right, so this is our inverse variation equation. But we also have some information that is given to us right here that will enable us to figure out this value of k that's relevant to this situation. Take a look at this part. It says the astronaut weighs 180 pounds at sea level, which is about 4,000 miles from the center of Earth. So, we're given that W is equal to 180 when the distance is 4,000. Now, in order to make this work out in a little bit nicer fashion, I'm going to think about D as being in thousands of miles. And so I can say from this part that if W is equal to 180, then we have D is equal to 4. So we'll plug in the 180 for W. And then we'll have K over 4 squared. Now, of course, the 4 squared gives us 16. And that means that we have 180 is equal to k over 16. But then we could certainly multiply both sides of this equation by 16. And on the left side, when you multiply 180 by 16, you get 2,880. And you multiply k over 16 by 16, you'll get k. So our proportionality constant is 2,880, and that number is going to go up top here to give us a more specific inverse variation equation. And so I'll have W is equal to 2,880 divided by d squared. All right, so we're making progress here. But the question we're trying to figure out, or the question we're trying to answer here, is how much does the astronaut weigh when 2,000 miles above the surface of the Earth? Now keep in mind that d is the distance from the center of Earth in thousands of miles. And so we go back to this figure and realize that if the astronaut is 2,000 miles above the surface, then the distance that the astronaut is from the center of Earth is actually 6,000 miles. So, with that in mind, what we're being asked to do is figure out what W is when D is equal to 6. So what we'll do here is we'll have W is equal to 2,880, and we'll put that over 6 squared. So we're plugging in 6 for D. Well, that's the same thing as W is equal to 2,880 divided by 36. And so if you take a look at the 2,880 and then you divide it by 36, then what you get is W is equal to 80. And so from this, we would arrive at the conclusion that the astronaut weighs 80 pounds when the astronaut is 2,000 miles above the surface of the Earth. Now at this point, I'd like to give you some recommended exercises from section 8.7. So the exercises will have 13, 15, 17, 19. Let's see what else. 31, 35, 37. And then 41, A and B.